First of all, thank you for coming. This room was very hard to find, and you guys made such a great effort, and thank you very, very much. So we are close also to lunchtime, and we're going to have fun. We are going to speak about satellites and space and maritime vessels and very, very cool stuff that we do with this, so thank you. But first, I must, and I want, to present my company, ImageSat International. Basically, everyone can hear me? It's okay? So basically, we are the only company in Israel that has our own high-resolution commercial electro-optic satellites. We was established in 1997, and our first satellite was in space in 2000. Then in 2006, we launched our second satellite, EROS-B, and is basically now is our working horse. Is 70 centimeter resolution, panchromatic satellite. We also an Israel new space leader, and we also develop small satellites like a shoebox. We call it Runner, and we're going to launch one of them next year, and it's going to be 1 meter resolution and in color. And afterwards, we will launch EROS-C, which is going to be very, very high resolution, 13 centimeter resolution, and also in color. So this is from the sensor side. We also provide end-to-end intelligence solution, and I'm going to show some of very, very cool example. In the end, I will show you how we detect a submarine in the middle of the sea, which is very, very cool. So please stay with me, and thank you. We also strategic vendor to Israeli MOD, and we use many AI techniques for our solution, and yeah, just let's see. So what we do, of course, we provide the satellite service. We sell satellite imagery. We also provide intelligence as a service solution. We not only sell imagery, we also get a meaningful, intelligent insight from this imagery. We also correlate it with many, many other sources. Many of you hear about us in the news. Satellite detect some activities in Syria and other areas and so on. This is what we do. Analytical solutions, this is basically my team. Both intelligent as a service do manually, we do it automatically. We develop algorithms that do all these things, amazing things, automatically and very, very quickly. A ground segment, we develop our next generation multi-satellite ground station. Space segment, which is basically a new space activity that we develop small satellites like a shoebox, and one of them is going to be launched next year. And of course, education and training. So let's talk about our problem. And our problem is that we want to detect a dynamic object with the satellite sensor. Dynamic object, basically the moving object. Okay? So in order to understand this challenge, let's first understand the satellite mission cycle. Satellite mission cycle may take hours. It very, very quickly, 4 hours, and we want to be there in 4 hours and less. But it's in average, it can take 6, 8, and even 10 hours. So what is the challenge? Here, there is a request for information. There is some location that we want to take a picture. Then there is the planning stage. We took all the targets that we want, that our satellite will take a picture, schedule, optimal scheduling, planning, algorithm will run there, and it can take few hours, actually. Then when the satellite is above our ground station, we can upload the task. Then it's cycling all around the world, and when it gets to the current location, it will take an imagery, and then when it is above our ground station, it downloads the task, the imagery to the station, and there is an analysis process that we do. And I will talk about this analytical process. It's also very, very challenging, and I will show you some example how we solve it. So this is the cycle. This takes several hours. Let's understand. So we have our target. When this our satellites, can I show? Okay. No, I cannot show it. So when the satellite is above our ground station, we can upload circle, 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 circle till it gets to the target. And when it's above the target, it gets line of sight with the target. It can take take a picture, imagery, and it downloads the data when it's above the ground station. So actually, it works very, very well on static targets. So it's worked for years, and we do very, very great result with this, and everything okay. But how we detect dynamic object? So this scheduling, this cycle take hours. When the satellite came to the location of my object, it's not there anymore. So what we do? So this is our challenge, how we detect dynamic object with the satellite sensor. But first, I want to convince you why we need this, why we just solve it. Who cares about dynamic object and space and satellites and so on? So let's take, for example, our maritime domain. We use satellites in maritime domain basically when other solutions, where other sensors are unuseful, which is in deep sea. In deep sea, there is no radars, there are no any patrols, aircraft patrols, there's nothing, basically. And we want to get meaningful insight what's going on in deep sea. The satellites are basically the only solution or most effective solution that we have in this far from the shoreline areas. What we are looking for in the sea, basically we want to detect all the non-cooperative vessels. Vessels that do not transmit any AIS signals. AIS is the automatic identification system. Any vessel, maritime vessel above some size, need to transmit its location and other parameters. But those who we are looking for, of course, will do the illegal activity, mostly not transmitting any AIS signal, or they can mislead about their identity. So basically they can tell they are just, I don't know, cargo vessel, but they are fishing vessel which perform illegal fishing right now, and those who we are looking for, those we want to detect. Satellite imagery provides us a visual evidence of the vessel parameter. This is very, very important for us just to get a proof. Okay, the vessel is there. It may not transmit any AIS signal, but I detect it with satellite imagery. I know that it's there right now. Satellite imagery, it's not a real-time system. We cannot speak about, okay, I knew the exact location of the vessel every minute, every second. No, but in deep sea I can say, okay, this is the vessel that you are looking for, and I know it was there 6 hours before. It's very valuable information, okay? And of course, our challenge, we are a commercial company, is provide a cost-effective solution. Use as many satellite imagery as possible to get what we are looking for. So deep sea is a huge, huge areas. Satellite imagery, it's a small one. So how many satellite imagery do I need to use in order to find what I'm looking for? We want to provide a very, very cost-effective solution to use as minimized as possible satellite imagery. Okay, so I cannot. Okay, sorry. So, no, can you see this? No. Okay, so this is an example. There is vessel that come from the point A and it come to the Limassol port. When it's close to the shoreline, it will be detected. It will be detected by radars. It will be detected by patrols, aircraft patrols, and other automatic vehicles that they have. But in the deep sea, there is nothing. If this vessel is not transmitting, okay. Wow, high tech. Okay, so this is the vessel. This is the route. Here, this basically. We are absolutely blind what's going on here. It's nothing there. To send the aircraft patrol to here, it's many times it's too dangerous. We will not do things like that. But satellites, is the best way for us just to know what's going on here. And if we want to track some vessel, want to detect some vessel here in these areas, satellite imagery is the best solution. But our challenge, if you remember, is to do it in a cost-effective way, to do with as little as possible satellite imagery. This is what we want to do. Just to understand the proportion, suppose this is the last known location of my vessel. In 12 hours, remember the scheduling cycle takes hours. In 12 hours, this is the uncertainty cycle that a maritime vessel can create. It can be anywhere here, anywhere. This, the proportion of satellite imagery. This is the one. In order to find the vessel in this uncertainty cycle, we need thousands of satellite imagery. Nobody will buy such system from me. Believe me, I tried, no. But suppose we will take into consideration the direction of the maritime vessel, the direction. So we can minimize it on hundreds of satellite imagery. It's still not very good solution. So what we do? We develop a very accurate activity prediction algorithm. We basically get 80% accuracy in 12 hours and narrowing the searching area in less than 3%. What we do, in short, we learn all the historical pattern of the specific vessel that we are looking for, of the other vessel in this area, of the similar vessel that behave in similar fashion, the vessel that we are looking for. We create a behavior graph. We put all this data that we know about the vessels on the behavior graph, all the stopping point and all the velocity and many other things. And it's a Markovian graph, and we use second order because we do not believe that the vessel transmits the destination that it's going to, so we use a second order Markov chain. And then, in order to calculate the intersection between the satellite's passes and the possible location of the vessel in specific times and so on, and what is the best satellite and what is the best opportunity window, and it is a highly complicated problem. So we use a multi-agent simulation, which is a very good solution for these kind of problems. And we actually create agents that each one, we have thousands of agents, that each one behave as one of the possible behaviors of the vessels. And we calculate the number of agents within the intersection with the satellite passes. So just go back to our example. This is the less known location. This is the uncertainty cycle, of course, it's not good. This is the satellite imagery. This is what we do. You see the proportion? This is our prediction. That's it. We predict that in 12 hours the vessel will be here. The blue one is the higher probability. There are much more agents was there. The red ones, another colors, is the lower probability that the vessel will be there. And we use, in this case, it's our use case, only on 4 satellite imagery, and it was there. This was the vessel that we are looking for, and we actually get accurate prediction and accurate detection of the maritime vessel in the deep sea. Okay, so remember the analysis process. So we know how to accurately schedule the satellite with the prediction algorithm and so on. It take a picture of our vessel. It download when it's near our ground station. Now, what about the analysis process? So manual analytic of satellite imagery may take hours. Why? The size of the imagery can be 10 on 10 kilometers, but it also can be 60 on 25 kilometers. The size of the object, it can be just few pixels. So the imagery is very big, and the objects are very small. To detect all of them manually, it's not a very good solution. And we give tens of such imagery every day, so it's not a very good solution. So we need to do it automatically. So we develop in my team automatic vessel detection, also classification, and also the identification of specific vessel that we are looking for. This algorithm take only a few minutes. Okay. So just take a look at the example. This is the satellite imagery, and these are the vessels. It's very, very hard to see in the eye. We need to zoom in. So we develop automatic vessel detection. We, of course, use deep learning. I will show you how some techniques that we use. It was not enough to detect all the vessel in the imagery. We also wanted automatic classification. Now, our algorithm now know how to distinguish between 45 different types of the vessel, and it's still learning. It's still learning. So we detect the maritime vessel. We also provide a very good classification of what type of the vessel. It depends on what we are looking for. If you're looking for military vessel, if this is our use case, so we want only that our system will show only the military vessel that it found. If we're looking for, for illegal fishing activities, so we want only the fishing vessel that it will show us. Let's take the example. This is a very huge satellite imagery. Okay, it's 25 kilometers on 60 kilometers. Automatic detection take only a few minutes, 2 or 3 minutes. Automatic classification, and look what we found here. Ta-ta! It's very useful information that there's some things near to our shoreline or something like that. Okay. It was not enough. So basically, one of our use cases, we needed to, I will show you this example also in the end. We needed to detect specific vessel on a daily basis for a few months. So it was very hard for, okay, so we have automatic detection, automatic classification, but we were thinking, okay, so let's just develop automatic identification. Let's find a specific vessel. Don't show me all the types. It's still too many. I don't know, it's 10, but I don't want to go over the 10 vessels. Just find me the specific one. So we teach our machine from 7 examples. It's a big number, I know, but we want to minimize. We are working on it just to do it only in few, 2 or 3 examples, if possible, to detect the specific vessel, to find the specific one. And here, actually, this was the real case. It was we also detect the meeting between this. It performs some illegal activity and the other small vessel. It's also a very, very valuable information to know about vessels. Okay, this is again example of satellite imagery. There is hundreds of vessels. The identification algorithm just mark me the more similar one to those who I'm looking for, and it just minimize the number to 3. So actually, the one that we are looking for was at 2nd place, but this was the 1st place. I don't know, for me it looked the same, but our intelligence team told us, no, it's, you're in the 2nd place, the 1st place is something else, so you guys should judge. So for our development evolution of the detection, classification, and identification of the maritime vessel, we first, of course, we use deep learning, of course. We start with semantic segmentation, and it actually worked very good for us, but when there is meeting between 2 vessels, the adjacent vessel cannot be separated. So it was a challenge for us. And also we wanted to go to the classification, so then we move to hierarchical classification, deep learning techniques. But now we're here. this is what we are working in these days, the instant segmentation, because we want automatically detect the meetings between two vessels. So, more example. This is satellite imagery, automatic detection, automatic classification, but when there is meeting between two vessels, we are now working on it. So our challenge was to detect, I will show you guys some examples, don't worry. I have very, very cool examples. But our challenge was to detect 2 minutes, I will do it in 1. Our challenge was to detect a moving vessel with satellite sensor. We closed the entire loop in less than 4 hours, from the target selection till the satellite's accurate tasking and the imagery analysis. We provide a very cost-effective solution. We do it only with 2 till 4 satellite imagery. It's very, very cost-effective solution. And basically, if you think about this problem, it's like finding a needle in a haystack. So detect moving vessel in the huge areas with less than 4 hours and only with few satellite imagery. This is what we do in the maritime domain. I will show you some cool examples. Remember, I promised you a submarine. So this is what we do. This was our last known location of the corvette that followed the submarine. How we knew is we had the intelligence lead about it. So we knew that somewhere in this area, the submarine will be up from the water. So we knew, so with our multi-agent simulation, we calculate the prediction and the satellite and where our satellite was in this specific time. And this was our prediction, 5 hours ahead. And we use 3 satellite imagery, and here it was, a submarine in the deep sea. Very, very cool. This is the corvette, actually, that followed the submarine. We do it again a day after for fun. No, it's not actually. Again, we knew the last location. We predicted the position with our algorithm, and here it was again, up from the water, a submarine in the middle of the sea. And actually, this is how it looked like. This was the first prediction, this was the second prediction, and accurate detection of the satellite imagery with our submarine. Another example, okay, very, very quick. There is the vessel that was smuggling oil, it performed something illegal. It transmitted AIS signals, but suddenly it stopped, and for 3 months, nobody knew where the vessel is except us, because we track it with satellite sensor, because this is what we do. And we did it on the daily basis. Actually, we predict where it will be and track it again and again and again. We actually can tell what was the last position that we know of the vessel that was interesting to some organization. Okay. Thank you.
Thank you, Natalie. We have time for questions.
Much earlier, you were talking about a cycle of 4 to 10 hours in order to send a message to the satellite to take a picture at a certain location and send it to the data.
Yeah, the satellite cycle, yes.
So I was wondering, how much would it add to the cost, basically, to take constant images and then and to download each time and just run over the previous data, so when you need to query, you don't need to wait for it to do the cycle?
Yeah, it's a good solution, but today it's actually not practical because we have huge areas and satellite imagery is something relatively small, so we don't know where just to take a picture, whatever. And also the download process, we cannot take a picture of all the data that we want, and we also cannot download all the imagery that we want. So this is still a challenge.
I have actually two questions. The first, you said about learning the historical data of the vessel.
Yeah.
But then you need to have this data coming from another source. Or if it's the first time that this vessel is being used.
The first time that vessel is used, it's it's not very common, but of course there's new vessels that come to the sea, of course, but then we also use the behavior pattern of the area and also behavior pattern of other similar vessels. So if it's a military vessel, we learn the behavior pattern not from AIS, of course, because they do not transmit any AIS, but from other intelligence sources that we have.
Okay.
So,
and also about the identification, you mentioned that the ship can be 4 on 10 pixels.
Yeah, very small.
So
in this case, we cannot identify.
Okay.
No, we cannot.
Okay, thanks.
You talk about these multiple agents
Yes.
in the prediction part.
Yes.
What are they? If you can answer.
They have their action.
What are they? Raiders?
No, agents. No, it's a small. It's a simulation of the ship with location, with possible path, and the possible velocity, and the possible turns that it can take. So each.
You actually build the predicted trajectories, so you don't just select from them, right?
We built multi-agent simulation that each agent can behave as one possibility of the specific vessel. And the action is actually the velocity and the route that they can take. And all the turns and all the stopping passes. So it's not a very smart agent, but it's still an agent which need to make some choices with...
Can you give information about how I'm here? Hi, don't you worry. About how you deal with so small segmentation on so big resolution image? Because pyramid, like what is the structure? Pyramid seems even not performing well on so small object. Like, do you slice the images? Can you give information about this?
Yes, this is basically our very huge challenge, and we succeed. We have you should remember, we have a very huge data sets of the satellite imagery. We have our first satellite was in space in 2000, and we have huge data set. So we have entire team that just mark the data for us, but yet when we start to teach our machine, we have a very bad results, but we improve. We don't give a full image, of course, just slide.
Thank you for this wonderful talk. Just a question about the input of the neural network you are using, and especially which wavelength there is in the network. Is it grayscale? There is also higher.
We use grayscale, but we are now also want to use these networks in color, because we also have color imaging.
Okay, which means it is RGB or it is
RGB.
wavelength?
RGB.
Only RGB. Okay. Thanks.
And we are hiring, so come to talk with me.
Thank you very much, Natalie.